Good afternoon, everybody. Thank you for coming here today. I'm happy to introduce Professor Peter Wadhams, visiting professor here at the Politecnico and also at the Politecnico of the Marche. As you probably know, Professor Wadhams was director of the Scott Polar Institute in Cambridge from 87 to 92. And he is emeritus professor of ocean physics at Cambridge since 2001. I think that many of you read his book, which was translated in many languages, including Italian, A Farewell to Ice, which is the story of the alarming trend of the disappearing of ice in Arctic and at the poles, and where he describes what the consequences will be for our planet if the Arctic ice continues to disappear at the current rate. So in his book and in his studies spanning throughout decades, Professor Wadhams has analyzed the dramatic consequences of this phenomenon, both at a scientific level and also at the economic, social, and environmental level that is turning now also geostrategic implications on a world scale. So I'm happy now to invite here Professor Wadhams, and I remember that we will have also like 15 minutes for questions and answers. Please, Professor, thank you.
Well, thank you very much. Here we are. Okay, my talk is called Ice and Fire because I want to focus today on two aspects of climate change and how they interact together. We know now from all the awful things that are happening to the planet that if one aspect of the climate is changed, it affects everything else as well. All parts of the planet are connected. So if something happens to ice, then there's an impact on brush fires and vice versa. So I'm going to talk about how brush fires and ice interact because both of them are found in Italy and we've studied them both here at Polito. So because of the title, it gives me an excuse to read a poem, which I seldom have the chance to do that. And this is a poem by Robert Frost called Fire and Ice. And so it reads, some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favour fire. But if it had to perish twice, I think I know enough of hate to know that for destruction, ice is also great and would suffice. I'm not quite sure what the words mean, but it's a very moving poem. Now, we start with ice, and I want to show you something of the ice sheet in Greenland and what it's doing at the moment, why is it melting fast, and what can we derive from our knowledge of visiting that ice sheet. So here we have the Greenland ice sheet near Kangerlussuaq, which is halfway between the south and north of Greenland. And I happened to be visiting it on a day which was quite famous because it was the day on which the largest single loss of ice from Greenland in a single day was measured. And that was 12.5 billion tons of ice was melted off in one day. And one of the reasons was it was very warm, and it is obviously what happens if you have warm weather, you have ice melting, and this was very warm. It was 21 degrees on that day in August 2019, and normally, or in the past, when I've worked in Greenland, the temperature has never got above zero, even in the summer. You don't have any melting, or you didn't have any melting on the Greenland ice sheet, and now you do. And so a temperature of 21 produced a lot of meltwater that day. It was just streaming off the ice. But there's a more, an even nastier thing that you see, which is a phenomenon that's only also been seen, started to be seen fairly recently, and this is called black ice. The way it works, and as you see the photo, the ice is black. The way it works is that the ice sheet in Greenland and in Antarctica is covered with dirt and soot. And one of the things we're studying is it mainly dirt which has blown across the continent, or is it mainly soot which has come from brush fires? And whatever it is, it coats the ice cover, and then when you have melt going on in the summer, then the meltwater drains away down through the glacier via various pathways, which I'll show you, which take it into the open ocean. So the ice in the summer is melting, draining into the ocean, but the dirt stays behind. The dirt doesn't go down with the ice. It stays to form an increasingly dark layer on the surface because it's staying there while the ice is going. And this is called black ice. It's not actually always black, it's more often brown. But here's some on the top of the ice sheet. You can get the scale by seeing the person in the background, my colleague. And this is really nasty, black, gravelly type material. Okay, a few more pictures of the ice during the summer on different days. Here, when the ice melts, at that time of year, there's now such a lot of melt that you get real, very rapidly flowing rivers of meltwater produced in the ice sheet, draining away to the ocean. And these are really quite serious. They've carried away bridges, for instance. And here we see a very violent melt stream, which in fact has worked its way down and through the ice, cutting its way down through the ice sheet, so that you can see the bedrock beneath. That's the brown material at the bottom. And this is all melted away and being carried off by this really rapidly fast-flowing river of meltwater. Then here's some other pictures where it looks different. This black ice has different appearances depending on the slope of the ice sheet. So here we see the bedrock again, the bottom of the ice sheet was moraine. Here we see a melt river which is flowing, taking the meltwater away. Here we see the ice, but it's lighter brown than the previous ice. It's still black ice in the sense that it's not white. White ice reflects radiation. This absorbs radiation and warms the ice up. This is on a shallower slope, and here underneath this is ice. So this is a thin layer of mud, which is on top of the ice. So the ice is melting, forming this Okay, the ice is forming this melt river here and flowing down underneath this muddy layer, which is dirt or soot, we don't know which. Then this is a really serious black ice because it's very thick. This is really earth, and this is because this slope is very steep slope between the ice sheet and the land, and this means that the black ice forms something like really a stable platform of earth. So this is, again, extraordinary. So this is the sort of ice we now have in Greenland, and it's really remarkable to experience these different kinds of ice which you get in the summer. So now we think about fire, the other aspect of the talk. And in fact, I experienced that actually on that same trip that I was driving through California after visiting Greenland, and we came across this pool of smoke on the highway, which we thought initially was simply a building that had caught fire. In fact, it was a canyon that had caught fire. It was one of the canyons that run into Pasadena from the mountains on either side. One of them was full of dried brush, which just caught fire, and we had this difficult to put out fire, which meant that the freeway was closed for 4 days, and everybody, this is a city, everybody was living in this city as if in the middle of a fire. Here we are, while the fire was still going on, they were trying to put it out. So this is Pasadena. When you think about towns in California that are burnt down by fires, you always think of small towns, but surrounded by forest. But in fact, it can happen with large cities as well, which is very worrying. Now, we move on up to the worst fire up to date, and the strange thing is that the worst fires that have been happening on the planet actually are in places you least expect to see them, and one of those is Siberia. You think, well, Siberia is very cold. It's also very wet when the permafrost melts. So you've got a cold, wet tundra, which you don't expect to be able to catch fire, but it did. And this fire lasted more than a year, and in fact, it may still be burning because it caught fire during the summer. It kept burning through the winter underneath the ice. You had a smouldering fire going on all through the winter. The Russians didn't do anything about putting this out because their view was nobody lives here, so we don't need to bother with it. But the trouble is that it released far more carbon dioxide than anything else happening on the planet that year. It released 505 megatons, and that's more than the total release of carbon dioxide from Britain in a year. And this was just that fire. And the area was 1.5 million hectares, which make it the largest fire in the world. So this was a very, very serious fire. Nobody was being killed, nothing was being damaged because there aren't any people, but still it was very, very damaging and nothing was done about it. This is the Russian theory of how to deal with brush fires, is you ignore them. And we can see why that happened, because the temperature of the tundra of Siberia has been rising far more rapidly than any other part of the world. We already know that the Arctic is the fastest warming part of the planet. It's 3 or 4 times as rapid in its growth rate of temperature as any other part of the planet. So if we look at the temperatures over the last 70 years in Siberia, we find that there was a little period here of low temperatures, and then from the year 2000 onwards, there was just very rapid growth and relative to the average, and it's now gone up 6 degrees warmer than the average temperature. And of course that was enough to dry off all the tundra and enable it to catch fire. And when we look at how much carbon emissions have occurred because of these fires, there's a lot of them. This big one is the most famous, the biggest Siberian fire, but there are lots of other Siberian fires going on all through the year. And this is a graph of the carbon emissions released by these fires. The biggest carbon emission was from this recent fire, which is probably still going on, and these are earlier fires. But there's a lot of carbon being released by Siberian fires, and no action is being taken. Now, still in Siberia, it's another kind of fire. It's that as well as the fire in the tundra, all of the forest and the tundra regions of Siberia are drying off, but at the same time, the permafrost which underlies this is a permanently frozen ground, is melting because of global warming. So we're having a material forming which is used to be frozen and is now melted, and a bit like it's a bit like the if you keep vegetables in the fridge and forget to switch the fridge on, they become green and soggy and horrible. That's what melted permafrost is like. And so this permafrost is very dangerous because it releases methane, which is a greenhouse gas. And a place where you can always find methane in the Arctic is a lake, because the bottoms of lakes have got methane being formed because of the rotting vegetation. So this is a Siberian lake, and they're demonstrating what it's like to have methane coming out of the lake, and of course methane burns. So here the scientist is setting fire to the methane, and to demonstrate there really is methane coming out of that lake. And if you have the chance, I think this will be a good film to see. It's called Ice on Fire. Everything is called Ice on Fire. It was produced by Leonardo DiCaprio, and it deals with climate change and carbon dioxide release. Everything that's important about the climate is dealt with in that film, and he travelled everywhere in the world to make that film. But one of the pictures is which they used to advertise the film, actually was done on the day that they had this release of methane. And in fact, this was the next thing that the scientist did, was he stuck his ice axe in the lake again, and this time the methane caught fire and set fire to his trousers. So DiCaprio thought that was a wonderful thing and made it the advertisement for his film. So it's an HBO film. You can find it on Netflix, or there's various pirated versions that you can find on the web. So that's ice on fire. Now I should explain why we were in Greenland, and it was a company that we were working with, and I'm chairman of their science committee. It's a company that runs races or rallies in remote parts of the world using electric vehicles, and this is the kind of electric vehicles they use. So the idea is that the racing in remote parts of the world will be accompanied by a science program to study what we are doing to these remote parts of the world, one of which is Greenland. And the other purpose is to induce people to buy electric cars, because if you can buy an electric car like this one and race around bashing people with it, it sort of inspires you to believe that electric cars can be fun as opposed to petrol-driven cars. So that while they were racing around the fjord in Greenland, we were doing scientific work. But in fact, the drivers who were in the race were really keen on climate change work. So the entire group of 16 drivers, there's 2 drivers for every car, a woman and a man, and they all came up onto the ice sheet and helped us by walking around picking up little samples of ice and dirt, which we can then analyse here at Polito. So here's the gang of scientific rally drivers, and this is the sample bottles we used. So they took hundreds of samples for us, so they were wonderfully helpful. And 2 of the drivers, this is Jensen Button. These were ex-Grand Prix drivers who decided that electric cars were better for the environment, so they switched to electric. And so Button is now a kind of champion electric car driver. And this is another leading driver, Kate Munnings, who does a lot of work on climate change research to help people. And just another shot of the top of the ice sheet where active melt is going on, and the meltwater coming off the ice sheet is running down very rapidly down towards the ocean. So you can see it's a very dynamic region. Now, we collected these samples, and a colleague who helped collect them is Giuseppe Alicino, who is a professor at Partenope University in Naples. He used to be my colleague at in the Politecni of the Marche, but he was on board to do sampling from the ship, because the whole process has a ship which goes from place to place, setting up for the races. And he also went up onto the ice sheet and helped by adding to some of the ice collection. And here he is up on the ice sheet. Then, as well as from Greenland, we wanted to look at the variation of ice and dirt, and so we did some collection from a glacier in southeast Iceland, Solheimer Jökull, and you can see it's different in character from the Greenland ice sheet. The Greenland ice sheet is 4,000 meters elevation. It's really high. This is relatively low, and so it will be warmer it ought to have a different character in terms of the relative amounts of ice and dirt. So this is the same glacier seen from another direction, and we can see that it's a low-lying glacier. So we might do more work in Iceland. As my wife did this work, we can look at the contrast between very high polar ice sheets and low-lying semi-polar ice sheets. Now, how much ice is actually dumped every year when it melts? And well, until recently, nobody knew. You had people who were studying ice, that is, people who call themselves glaciologists. The only way of measuring how much ice is produced in melt is to stick a stake in the ice. You have a bamboo stake, put it through the ice, and then measure how the level of the ice against the stake changes. That's a very crude method. But now there's a wonderful instrument called GRACE, which is Gravity Recovery and Climate Experiment. It was designed by NASA and the German Space Agency. And the way it works is very clever. In fact, it looks like a UFO. In fact, what you see are two instrument packages with a microwave measuring instrument between them. Each of those is launched so that it's flying very close to the other one and parallel to it. So they fly around the world like this, and when they come across a change in the conditions of the planet, that is to say, a change in the rocks, a change in the elevation of the Earth, then it changes the orbit of the sensor. And in particular, if you've got these two sensors flying together and they come across the edge of a continent, like the edge of the Greenland ice sheet, then the one in the front will speed up because gravity is stronger over mountains. So you have the two going together. The first one speeds up as you cross the Greenland coast. The other one falls behind. And then as you cross over into the interior of Greenland, the second one catches up with the first one. So the distance between the two sensors changes as you cross mountains, coastlines. And this is measured very accurately by this microwave sensor. And it enables you to actually calculate the mass that you've passed over. So you can calculate the mass of the Greenland ice sheet, the mass of the Sahara Desert, the mass of anything that's sitting there on the Earth's surface. It's a wonderful device. And of course, it's ideal for measuring glacier surfaces and telling you how much ice there is in Greenland. That's something we were never able to do before. And here we see some results. Firstly, the map of Greenland is showing a mass change, which is positive in the middle, that's the white area, and negative around the edges, which is the orange and brown. So the edges of the Greenland ice sheet are retreating, but the centre is growing. And that's because the edges are at a lower altitude, and so they're at a warmer temperature, and they're losing mass. But all told, there's a loss of mass. There's more mass being lost than being gained, and that gives you this curve here, which shows. This shows the annual loss of ice, and it's quite a steady loss of about 277 gigatons, that's billions of tons, per year. And so Greenland is losing mass steadily and consistently, and that ice will eventually all go away and there won't be any ice left in Greenland. Also, of course, one of the other reasons, or one of the main reasons this is happening, is because Greenland's warming up. And here we have, very often you have extreme events where you can get a huge amount of warming, which then produces a lot of melt. So here, for instance, was an anomaly that happened just last month, in September, and the dark red here is unusual heat. And so there was an unusual heat all over the Greenland ice sheet, and the anomaly was about 14 degrees. So if you went on to Greenland in September last month, you'd find the temperature 14 degrees warmer than the average, which is even warmer than when I was on it. So we can see how the changing in climate is producing really big impacts. And these are just some of the things you see when the ice is melting. You find melt pools occur all over the ice sheet and connect themselves up and then flow down in they form rivers, and I showed some pictures of those melt rivers running down to the sea. If there's nothing much there to hold you, there's lakes that will hold the water, and these things are called moulins, and a moulin is a big hole in the ice sheet that goes right down to the seabed, right down to the ice, to the bed of the glacier, and it's because water pours down those holes during the summer, and if you're not careful and you fall down one of those holes, you're dead. And sadly, one of my friends, who was a very great glaciologist, died last year when he fell down a moulin. And you can see a sort of, even when you haven't got the ice flowing away, it forms little patterns, connected patterns like this. Then you get to the coast. Firstly, most of the ice goes downwards and flows through the material of the ice sheet and ends up going out to sea somewhere. But some of it reaches the edge of the continent, and then you get these kind of impressive flows of meltwater that burst their way through the ice sheet to the land or to the sea. This is northern Greenland, Pitufik, and this is the ice sheet in western Greenland has got huge crevasses, that's fissures, that's these big gaps here where the ice is broken up by being moving out towards the sea. And then, of course, the water takes its opportunity to flow down through those gaps and produce these sort of dramatic waterfalls. And that means that the ice disappears even faster. So this is a really dramatically dynamic system. Now, the melt that I said happens, which I said didn't used to happen at all, this is the extent of it now, or this year, is that only the centre of the ice sheet is the only part that hasn't had any melt, because it's high elevation. But all around the edges, or the lower elevations, there's a lot of melt going on all the time, or a lot of the time, and here we see up to 100 days of melt during a given year. So we can see that the Greenland is disappearing fairly fast. And the result is, of course, the water has to go somewhere when it melts, and so it flows out to sea through these various melt channels, and you end up with a rising sea level, which is another big problem for climate. And we know that now there's more sea level rise occurring because of loss of ice from Greenland and from Antarctica than there is from warming of the ocean. In the past, we used to believe that sea level rise was due to warming of the ocean. When the ocean gets warmer and its temperature rises, the density of the water gets less and the ocean slowly rises. And this was how the ocean mostly rose in height, but now it doesn't. It's mainly now water flowing into the ocean from the continents, from Greenland and from Antarctica. And so the rising sea level now is something that's being added to the ocean, and of course will continue to do so. So here's the latest curve, and a thing that to remember is that things are worse, or things are always worse than you think they are. And one of the things that's bad with sea level rise, and also you find it in something like Acqua Alta in Venice, is that if you consider just a point on the ocean surface, here, let's consider a point here, then the elevation of that point varies with time. That's this bell-shaped curve because of tides, winds, temperature changes. If you sit in one spot on the Earth's ocean surface, its elevation changes. Then that's okay, but supposing you then add more water from the melting of the ice sheet. When you melt the ice sheet, you add more water, the average goes up. So if this is the mean sea level, the peak here, you add some water from the melt of the ice sheet, you get this point over here. You get this point over here, and the distribution of heights of the sea, it takes on this new set of values, which are the dotted line. Now, supposing you're in a place where you're liable to flooding, for instance, again, Venice, or any of the bays in the middle, in the Far East, a certain amount of increase in height of the mean gives you a much increased probability of flooding. So here, for instance, if this is how things normally are, then the probability of a flooding event might be just quite small over here, where the height is greater than the average. But now, if the mean goes up, the probability of getting a height well above the average goes up even more. So you have a small rise in sea level can give you a big rise in the probability of a flood. So places like in India and Vietnam and Europe, you're going to have more frequency of flooding and greater amounts of flooding. Then we come on to, we've talked about ice, and I talk about fire. And this is a town in California that was destroyed by a brush fire. And the same thing didn't used to happen in Italy, but now it does. And there was a very serious brush fire outbreak in Oristano, Scenariolo, in Sardinia last year. And in fact, next week I'm going back there we've got a research project going to try to see how we can restore the destroyed trees. And this is something where we go fairly frequently. So we're going up again next week. What happened was that you have mainly olive trees. There were forests of other trees of which the eucalyptus, the eucalyptus trees, which you don't think of as an Italian species, but actually they were planted in large quantities by the government of Sardinia because they grow very fast, and this was producing timber very rapidly. The trouble is they also catch fire very easily, and so there was a big loss of trees from that source, but also mainly very ancient olive trees were disappearing. And here are some of the sad sights of olive trees that are blasted out of existence. This is all in summer, not winter, so these thought to be in leaf. And what we're trying to do now is replant, and the trouble is that the heat from the fires was so great that it was burning its way down through the roots of the olive trees. So even ancient olive trees that have been there for hundreds of years were just disappearing through being burnt down under the ground. So here's, for instance, they've just dug up the underground part of the bark of an old olive tree, and we're trying to plant some more olive trees. So there's a company, a foundation called Medsi, which is working on this, and we're working with them. Okay, so this is the stump of what used to be an olive tree, and here's an olive tree where it burnt right down under the ground, so the only way to get it out was to cut it up into pieces. And here's a more normal landscape. Still, potentially some of these trees might survive. Anyway, that's what we've been doing with fire in Oristano, a place where, again, you don't expect to have forest fires. So what we've been doing in Polito is analysing the ice and the dirt samples to see just what they're made of. I mean, our concern is this ice, is this dirt that's being deposited all over the ice sheet, or is it soot? If it's soot, it's a different composition from dirt, and it's soot that comes from brush fires. So what's the origin of the material that is covering the Greenland ice sheet? So we've been doing this using this analyzer in Polito, and as my colleague Vincenzo Reggio has been doing this work. So at the moment we just test for 4 elements. That's carbon, hydrogen, nitrogen and sulfur, but the next stage in the analysis will be done with looking at all the elements, and so we can really see what's going on. But at the moment it seems that nitrogen and sulfur are not found in this material, but but hydrogen and carbon are. So it looks like the composition is largely carbon, hydrocarbon. So it looks like it's soot rather than dirt. So that's going on at the moment, and here's what we're doing. And we found, here we are, it's bigger numbers, that always there's no nitrogen and no sulfur. That's strange. And the carbon-hydrogen ratio seems to be fairly fixed. Where you have a lot of carbon, right up to these higher figures in Iceland, then you get higher hydrogen values. So the ratio seems to be fairly steady. So it does imply hydrocarbons being involved. So that's work that's still in progress. Well, I better be finishing here, but I should say something about COP27 because it's going on at the moment, and what do I think is happening? Of course, the person who's really most dynamic in pushing for action here is Greta Thunberg, still, and the horror story. I just have 2 slides to show the horror story of what's going wrong. Is that we've been measuring carbon dioxide emissions, or carbon dioxide content in the atmosphere ever since 1958 at an observatory in Hawaii, Mauna Loa, and it's just been going up all the time. This is 1958 to now. It's gone up from 280 to 420 parts per million. That's an increase of about 50%. And you can see the black is the trend, the red is the seasonal variation. But it just keeps going up, and it's accelerating. It's the exponential increase in carbon dioxide level. There's no sign that the carbon dioxide level is coming down. It's going up faster and faster. And it's a really kind of the curve of guilt is what that man should be doing something about this, but isn't. And the ultimate curve of guilt is the COP meetings. There's a COP meeting every year, and plus special meetings of the UN, IPCC, to come to super important, very, very serious agreements which every nation in the world signs up to and then ignores. And so here's the CO2 level in the atmosphere. Here's the milestones of great agreements, of which the most recent was the Paris Climate Agreement, and there was the Rio Summit back in '92. So we have these major international agreements, and in between, every year, there's a COP meeting, a committee of the partners in the UN, and they're supposed to agree on doing something, doing better, improving their targets, and so on. But if you look at each COP, you don't see that they made any difference to the curve of rising carbon dioxide, and I fear that COP27 won't either. So we know what we need to do to get rid of carbon dioxide out of the air or to reduce its use, but we're not doing it because it would be too much of a serious disruption to making money. So this is unfortunately, this is the shape of mankind's curve, and it will keep on doing this as far as I can see. The CO2 level will keep on rising exponentially unless we really take it very, very seriously, which we're not. Okay, so I'll stop there. I won't say any more about this. If anybody wants to ask me any questions about carbon dioxide removal. I've got a couple of slides I can show, but this is what I have to say at least about ice and fire and how they mingle together.
Thank you, Professor Wadhams, for this very interesting speech and for the dramatic scenarios that you described to us. So I suppose that since we have a few minutes left, if any one of you is liking to ask any question.
Thank you for being here, Professor Wadhams. So my question is that, like you mentioned, the politicians and countries tend to be like a little ignorant about the climate change issues. So do you think one of the reasons can be the fact that scientists sometimes lack to communicate well with people?
Scientists like to...
do you think one of the reasons can be that like scientists don't communicate well enough with the public?
Oh yes, I think that's true. Very often scientists, they don't want to stick their necks out because it might affect their career prospects. It might affect... It might be that they'll be shown to be wrong, and that's a terrible thing if you're a scientist. There's lots of things that make scientists less forthcoming than they should be. I mean, they should be shouting from the rooftops what's happening to the planet and that we have to do something immediately and then do it, rather than like you have people who make very stirring speeches like Gutierrez about we have to do something or we'll be in hellfire. But then having said that, he goes off and has a nice comfortable lunch in Brussels or something. It's not being taken seriously enough to bring about action, and you need to bring about action for taking carbon dioxide out of the atmosphere or reducing carbon emissions. These have to be done rather than just talked about. But scientists tend to just talk about them, or sometimes they don't even talk about them. So I think the world is being let down by a lot of its scientists, and we all need to be much more fervent and try to actually get some things done. The way that, for instance, Polito does do things itself. It's working on carbon dioxide removal from the atmosphere. So it's not just... So Polito sets a good example in doing things that really will make a difference to climate.
Excuse me, you said, I don't know, maybe I missed it, you said exactly that you find a soot produced by fires, for example, in California, in Sardinia. These soot particles have been found in Greenland, for example.
Yes, that's
the circle, the vicious circle.
Yes, it's they're transported by winds and deposited on the ice sheet. Mm-hmm. And so you previously had mainly dust from the Sahara and other parts of the world blowing over North America, but now you have soot from the forest fire, from brush fires. I mean, there's endless brush fires now in America. When you see a typical summer, there's always some huge fire burning somewhere, and this is all really new.
And they end up in Greenland.
In Greenland. Well, they end up in lots of places, but Greenland is a big receptacle because it's the world's second biggest island, and all that nice white surface just ready to be covered with dirt and soot.
Thank you.
Thank you. So unfortunately, our time is over, and I thank you very much, Professor Wadhams, for your speech and also for your call to action. So let's hope that mankind and leaders at the COP27 will hear the warning of scientists. Thank you very much, everybody, and thank you, Professor.